Tsai. So today I want to present the automated Whitebox Fuzz testing. So before diving into the paper, I will go through the key feature about this paper and the background knowledge, then the system introduction, and finally I'll tell you about the result and conclusion. So the motivation of the paper is that the traditional way of fuzz testing is using randomly mutate testing input. The limitation of such a method is that it cannot discover the edge input cases that might have buffer overflow flaw. To overcome such a limitation, the author developed a novel fuzz testing that can dig out more vulnerabilities that would cause the flaw of the buffer overflow even without having the input format knowledge. So the main contribution of such paper lies in follows. The SCAGE, which is called Scalable Automated Guide Execution program, can find large applications bugs in an efficient way. It also provides better code coverage than the black box fuzzing technique. So let's talk about the background knowledge of the paper. So let's use the lab program to illustrate the dynamic task generation process. This code is checking if the input string passes to the function top has a certain combination of characters. The input string should have 4 characters, and it's stored in the array input. So the variable cnt is initialized to 0 and will be used to keep track of the number of matching characters to find characters found in the input string. The first if statement checks if the first character in the input string is B. If it does, the count variable cnt will increment by 1. So on and so forth. So the second if statement is just check whether the second character is equal to A. If it does, the cnt variable will also increment by 1. The third is to follow similar logic, so it will check the third character. If it like equal to D, it will increment the cnt variable will increment by 1. And if the fourth if statement will check if the fourth character is equal to this mark. If it does, the counter cnt will increment by 1. Finally, if the count variable is greater than or equal to 0, the function will call abrupt and call the issues. So from this program, we can know that okay, to generate a dynamic text generations, the right hand side just demonstrate how do they generate the test case. So the leftmost case is self-defined string, which is called good. So as long as the left hand side is like no modification. For instance, if this string just tell us that it modified the last string to fulfill the last the correspond if statement. So follow the logic, we can know that wow, it will generate a GODD, which is follow the rule of the second position, the third position acronym, and then just fix the original test input to meet the criteria, and so on and so forth. So the rightmost side will be the most correct answer to generate the case. Okay, so let's talk about the limitation of the dynamic text generation. So the first one will be like the path exploitation. As we can see the previous slide, let's talk about the test case generation. We can find out that even we have like 4 if else statement, it will cost like to generate lots of test case. So in that scenario, it will be too many execution paths they can make that makes the analyze more difficult. And another issue about this testing generation method is that imperfect symbolic execution. So symbolic execution is imprecise in large program because complex program statements that are hard or impossible to reason about the symbolic at any reasonable precision or cost, such as pointer, manipulations, and arithmetic operations. So let's talk about the generational search. So the key feature is that it will explore the large application state space systematically and partially. And the optimization's symbolic execution, it will also optimize the symbolic execution while avoiding the redundancy. So symbolic executions always takes a lot of time to execute. So the generations search adopt a novel approach to separate the task between symbolic and other operation tasks. And it also can maximize the code coverage based on several heuristics. And finally, it also adopts the divergent resilience. So what is divergence? Whenever an actual execution path does not match the program path predicted by the symbolic execution for a given input vector, we say that a divergence has occurred. So let's talk about a generational search algorithm. It mainly composed of two programs. The left-hand side is a search algorithm, and the right-hand side is like a cascade expansion algorithm that will like expand the test case. So the important thing here is that the initial input seeds play a vital role in the search strategy. If it is well-formed, then it will help the search to discover the bugs more efficient and throughout. So let's discuss the algorithm part. For the initialization, the search algorithm uses predefined input seed and validate the input by executing the fuzz testing. At the moment, the first seed input will decide the performance of the code coverage and the depth of path. As the research iterates through them, you will expand them with an expansion algorithm. Yeah. So the expansion algorithm would expand all the constraints in the current path constraint to maximize the new input test. Then use a new expand testing input for fuzz testing. After that, the score function will evaluate each new input and compare it with all previous inputs' block coverage performance based on their own. To evaluate the input code coverage, the score function executes a new input and compare to all previous runs to compute the incremental block coverage. The novel part of the research is the expansion execution part. It maximizes the number of new test inputs to generate from each symbolic execution. To avoid redundant sub-search that overlap with the existing search space, the path constraints were implemented. Additionally, it adopts a backtracing limitation called bond to limit the level of backtracing. The two syntax here, PC something else, and this one, will show whether the current path constraint is included in the PC and also not in the PCJ. To achieve so, the author implement the path constraint which is corresponding to the symbolic variable that a conditional statement. So let's talk about the system introduction. So the program is called a Scalable Automated Guide Execution, which called SAGE. The feature is that it can test any file reading program running on Windows. By treating bytes read from the files as symbolic input, Sage can test any file reading program running on Windows. It can also perform symbolic execution trace in x86 binary level and it also can perform a general generational search. So the four components for Tsai to perform a general search will be as follow. There will be like four components in the Sage. The first one is the tester task. The tester task, it will detect if it detects the error, it will detect whether there's a certain error. If it does, it will set the task and perform the automated trace. And the second task is called tracer task. It will record execution log for each run. The third is called coverage collector. It will compute which basic block were executed during the run. During the run based on the recorded execution. This information usually is used for function score. And the symbolic executor, by replaying the record execution once again, this time is to collect the input related constraint and generate new input using the constraint solver dissolver. So let's talk about the block coverage heuristics. So the main goal is that it will help the program to deal with the divergence issues. So the divergent issues may hinder the search process. And the second thing is that the traditional port is like based on the depth first search. It uses a depth first search that occasionally picks the next child to explore using a block coverage heuristics. So the generational search approach, it tests and evaluates all the children of each expanding execution. So let's talk about the trace-based x86 constraint generations. So the reason for adopting a machine code-based approach is that it will have a multitude of language and build process. So the multitude of language is difficult to conduct the Fuzz test uniformly, since each language has its own compiler and building process. Machine code-based approach only need to implement once according to different chips architecture. The second thing is that availability of source. Machine-based level won't have issue with looking into the source code. And the final one is that the compiler and post-build transformations issues. The symbolic execution on the binary code will affect the originality of the program, which is that is because some of the code contains code obfuscator and basic block transformation during the compiling process. So there are two reasons to adopting offline trace-based constraint generations. So the majority of the components are protected by the operation system, which make it hard to replace the instrument versions. As for the non-determinants in large target programs, it makes it hard to debugging constraint generation online. However, by utilizing offline method, Sage could capture the outcome of all non-deterministic events encountered during the recorded run. Talk about the constraint generations. So before knowing the constraint generations, we have to know what is a symbolic tag. So what is a symbolic tag? So symbolic tag is an expression to note the input value or functions of some input. For instance, input M. So the goal of the symbolic tag is to storing the register to maintain the symbolic state of the program. So such methodology support tag as follows. So the input M, which means the nth byte of the input. The C is stand for the constants, and T operation with T2, which means the arithmetic or bitewise. Okay, let's talk about the stage constraint generation mechanism. So every non-constant symbolic tag is associated with a unique symbolic variable, and tags refer to both. Each time Sage replaces a recorded program trace, it continuously updates both symbolic and concrete stores. Additionally, addition to symbolic tag propagation, Tsai generates input value constraint. A constraint is expressions that define the relationship between symbols. So let's talk about examples. For instance, if the symbolic variable, we call it x, represents the fifth byte of the input, we tag as the input 4 here. The constraint x smaller than 10 means that this fifth byte of the input must less than 10. As soon as the algorithm encounters a conditional jump that depends on the input, it adds a constraint that models the possible outcome of this branch to the path constraint. Let's talk about the symbolic tracing and constraint collections. So the core starts by reading a file that is 10 bytes long into computer memories. Sage keeps track of the memory locations and links them to the symbolic tags, which are like the labels for each memory locations. So the first line instructions, which moves the value 10005 memory address into the register, we call it register called EBX. In this context, the EBX is being used a memory pointer, which points to a location in the computer's memory. The second instructions load the value stored at the memory locations, pointed to by the EBX into register AL. The by EBX syntax is used to access a single byte of memory. So the third line instructions decrement the value stored in the register AL by 1. And the final instruction is a jump instruction that transfers the control to label for 0. If the value stored in the register is 0, the JS instructions stand for the jump if 0 will execute. So in essence, this code loads a value from memory into the register AL, decrement the value in AL, and then check if the result is equal to 0. If it does, the control is transferred to the label for 0 jump. The first is an example about this demonstrate how they do. So the first line instructions is move a single byte of the data stored at the memory location, specify the back bracket into the high order 8 bits. We call it CH. And then the second instruction is move a single byte of data at the memory location, specify the bracket into the lower 8 bits. We call it CL. So the third instruction is means that it increment the value stored in the register CX by 1. In other words, it increase the value stored in CX by 1. The common increment CX is a human-readable explanation of the purpose of the INC CX instruction. Overall, these instructions are manipulate two separate bytes of the data, combining them into a single 16-bit value stored in the register CX. The value stored in the CX is then incremented by 1. So the symbolic subtag will work as follows. The CL will tag it as a T1, the CH will tag it as a T2, and the CX execution will a CX variable will be stored as a T equal to big parenthesis bracket with the T1 and T2 plus 1, and it only affected the CL values. So in a symbolic store, so following by this logic, the C1 will be subtracted to T comma 0, which means that and CH will be subtracted to like T comma 1. So that's a subtracting mechanism demonstration in this slide. So let's talk about the constraint optimizations. So the goal is to optimize the speed and memory usage of the constraint generation to make it more efficient and less memory usage. So let's talk about how dynamic task generation strategy. The first strategy is called tag caching. So it identified the same physical object by mapping the structurally equivalent tag to it. The second is called unrelated constraint eliminations. From the constraint solver queries, all the constraints which share the symbol with the neglected constraint will be removed. Okay, so let's continue the strategy used by the dynamic text generations. So another approach is using a local constraint caching. So it is skipped if there is already a constraint in the place. And there's strategy called flip comp limits. So a constraint can be flipped a maximum number of times before it's set to a maximum value. And the final one is called concentrationalizations, which is a symbolic tag can be converted into a concrete value by using a multiplex and bitewise operations. Let's talk about the SAGE strategies. So the goal of the SAGE strategy is in order to avoid running out of the memory and avoid having a redundant constraint for solver queries made by the SAGE. How do they do it? If the constraint is removed, it implies that such constraint is already generated from the same instructions. Yeah. So the example code procedure will be like that. Byte will be load several bytes into the memory register called C1 and start the loop until the value C1 becomes 0. In this program, the memory is linear. Suppose the MOV tag is mapped to tag T0. The generated constraint will be represent like a T1 till TK, and the K represent the load bytes. The subsumption technique allows us to reduce the K-2 constraint by analyzing whether the preceding tag is qualified to achieve constant space behavior. The constraint subsumption must in conjunction with some constant folding during the tag creations. So let's talk about the constraint folding mechanism. So the downside is that it cannot merge a constraint that is semantically unique but semantic redundant. To overcome the constraint folding issue, the sequence tag simplification is introduced. It creates a specific tag called subtag that map all the move instruction with the designated byte size. After that, it will conduct constant folding into a T, avoiding duplicating equivalent tags and enabling constant folding. So let's talk about the results. So the author noticed that the symbolic execution is much more slower than the tracing and task time. It shows that the separation of the task from symbolic executor task is really helpful to let the generational search optimize the symbolic execution efficiently. The main reason why generational search outperforms the depth-first search is that lots of the search algorithm follows a same way of testing case generation, which neglected symbolic execution time cost. Therefore, under same time constraint, the generational search can have more code coverage and spend less time for the search. The high divergence rate may be caused by the incomplete of x86 instructions simulations. The emulation only included nonlinear operations such as multiplications, division, and bitewise arithmetics. So different files and different bugs. As each search is incomplete, so it's important to use wide variety of such files to dig as many bugs as possible. So let's talk about the bugs found are shallow. The high divergence rate may be caused by the incomplete x86 instruction simulation. The emulation only included a nonlinear operations such as multiplication, division, and bitewise operations such as multiplication, division, and bitewise arithmetics. The no issue by generation illustration shows that there are a lot of test cases that were tested in large generations without any issues, but reveal any notable new bugs. As a result of this behavior, the experiments considered show a bell curve, especially in the histograms. So the figure 7 just shows that the overall well-formed file seeded the Sage search performance almost have a higher rate of the crashes than the seeded with the bogus. To ensure the higher rate of the hitting the crash point, well-formed file play a vital role in starting as a starting point of fuzz testing. For the WFF-4 seeded graph, we can obtain that there is a correlation between coverage and finding new bugs, but not universally. As for the WFF-2C illustration, even if the code coverage increased later, they found all unique bugs early. So the result proved that they are wrong about making the assumption about the correlation between the code exploration and new bugs discovery. Even if the code exploration is large, doesn't imply that the discovery of the bug will also increase as well. So the conclusion is that a new search algorithm called generational search was introduced. It's a better level divergence tolerance and optimal expanse on symbolic executions. A well-formed file is essential for discovering new bugs. Suggests a new search strategy. By utilizing the C file to generate a small amount of the test case, when the test cases are exhausted, move on to the new C file. Thank you for listening.